Okay, continuing with section 1.3. So we saw what do we mean by having writing B as a linear combination of some given vectors v1, v2, up to vn or vk, and we saw that solving that problem or answering that problem is equivalent to answering that these or solving the system of equations. Now the next thing is the geometric description of span. So we just saw what span of u1, v1, v2 up to vk means. It means the set of all the collection of all the vectors that can be written as a linear combination of the given vectors v1 up to vk. As mentioned before, it's actually not even possible to think about higher dimensional spaces or 4 or R5 or R6 or even higher to visualize them. So what we do, we look at spaces where we have two-dimensional space R2 and R3, the three-dimensional space. So in these two spaces, we can visualize these vectors and their scalar products, their addition, and now the span. So if we have a two-dimensional space R2, if we are in R2 and we have a vector u, then the span of u is set of all scalar multiples of u. So this will give us a line in R2 through the vector v and through the vector 0. What does that mean? It means the origin and then the point we have the vector v and all the other vectors that lie on that line, which will be the scalar multiples of the vector u. So here, let's look at this example. So we have this vector u. This is figure 1. Okay. So if you think of 2u, how will that be? It will be just an extension of this much. This is 2u. And similarly, if you want 3u, just extend it and the same amount. So this is 3u and so on. You can keep extending. Whatever negative u, it will be a vector going in the opposite direction, but of the same length. This will be negative u, and now you can have negative 2u and so on. So we can negative half u will be this much. So you can see there is all the possible multiples of u. So we get this line. So this is span u. Write it a little bigger. Span of u. So in R2, span of one vector is the line which contains the vector. Okay. Over here, if we have two vectors u and v, and they are both non-zero vectors in R2, and with v not a multiple of u, so u and v are not multiple of each other, then span of uv is R2. So then span of uv is the whole plane R2. So R2 means the horizontal plane. So here we have the vector u and v. This is v. So you should know the negative v will be a vector in the opposite direction but of the same length. So let's say this is negative v. So negative u will be over here. Okay. So now we already saw that one vector gives us the span of one vector will be the whole number line this, and the span of the v vector will be just this number, this line. Now what about span of both vectors? So notice here that if you want to find multiples of in the linear combinations of u and v, so for example you can look at what does u plus 2v looks like, or 2u plus v, or you can take higher multiples as well. So let's look at u plus 2v. So u, so I need 2v, so it means I will have another one over here. So now if I complete a parallelogram, so my final vector will land somewhere here. Okay, now we look at 2u plus v. So now I have 2u, so it means we are here, and v is over here. So I complete my parallelogram law rule. So my vector will end up here. So if you notice, all the linear combinations of u and v with c1 or all vectors of this type, where c1, b, c2 are positive numbers, then we land up in between u and v. So we end up in this region. But if I take all the linear vectors such that c1 is, so c1 negative u plus c2 negative u b, then we will end up in this region. So this is negative v, that is negative. If you look at all the linear combinations c1 u1 plus c2 negative uv, we will end up in this region. And then the same thing we will, so it covers a whole plane. So that's why we get the whole plane. In the same way, if v is a non-zero vector in R3, then the span of v is the set of all scalar multiples of v. And so this will again give you a line which is passing through 0, and it is containing the vector v. So this is how it looks like. It's again a little harder to show it in the plane, a three-dimensional object, but just roughly this is how it will look like. In the same way, now if we have two non-zero vectors in R3, then the span of those two vectors will be actually the plane R2, which is the plane which contains the vectors u and v. So note here u and v. So u is over here and v is here. So we have a plane which is not horizontal plane, but it is a plane at some angle to the horizontal plane, but important thing is that it passes through the origin. Now notice here, this will not be just this piece. Plane extends to, has infinite length and infinite width, so it is extending actually in every direction. This is just like a piece of the plane that we are showing. So this is what the geometric interpretation is. So you have to remember this. You can be asked in a definition, what is the geometric interpretation of span of UV? So what you will call that this is, so the span of UV means all linear combinations of U and V. So this gives you a plane in R3 passing through the region, through the origin, and containing U and V. containing u and v. That is what span of 2v is. So now we look at critical examples. So the first one is saying determine whether B can be written as a linear combination of vectors v1, v2 and v3, where v1 is this vector, v2 is this vector, v3 is this. This is actually the example we saw before, but at that moment I did not solve it. I just showed you that the linear combination gives us the vector equation, and solving the vector equation is the same as solving the system of equation. So that's what we are going to do now here. So what is a solution is that we want to actually find scalars c1, c2, c3 such that c1 b1 plus c2 b2 plus c3 b3 is equal to b. But what does that mean? That means solving a augmented matrix like this, and I just perform the row operations and I've got it into row reduced form. So this is the row reduced echelon form, and from here I can see that this system is consistent, and we have the value c1 is equal to -13, c2 is equal to -9, and c2 is equal to 3. Now we are not very much interested in this solution. We are more interested whether the system is consistent or not consistent. So since the system is consistent, so yes, B can be written as a linear combination of the vectors v1, v2 and v3 given. Second example, determine whether B can be written as a linear combination of vectors a1 and a2. Well, this is a2, sorry. And where a1 is the vector 1, -2, -5, a2 is the vector 2, 5, 6, and b is the vector 7, 4, -3. So again now, because we are given two vectors, we are trying to see if B can be written as a linear combination of two vectors. Now notice here all these vectors are in R3. So in the previous case also these were all in R3. So we were looking at if B can be written as a linear combination of three vectors. So we can also be doing this. We are in R3, so our vectors are of length 3 by 1 or size 3 by 1, but we want to see if we can write the vector B as a linear combination of just two vectors. So what does that mean? Solving the augmented matrix here. I hope you can see how I wrote the augmented matrix. First is the A1 column, then we have the A2 column vector, and then we have the B column vector. So applying the row operations, I got here to the reduced echelon form, row reduced echelon form. So what I get from here is that C1 is equal to -3 and C2 is equal to 1. What does that mean? System is consistent. So yes, B can be written as a linear combination of A1 and A2. Not A1, A2, A3, but A1 and A2. Last example, determine the values of K for which the vector Y is in span of AB. So again, remember to find out or to determine whether the vector Y is in span of AB. It means we are looking for, or we want to find scalars such that this is true. But what is this? This is a linear combination of A and B. So it means we are looking to solve this augmented matrix. So first column is 1 0 negative 2 because the vector A has those entries. Then the second column is negative 3 1 8, and the last column is K negative 5 negative 3. So now again, because my second row in the first column, it's the first entry of the second row is 0, so we are good. Some of our work is already done there. So we only have to now make this 0. So I multiply row 1 because this is the pivot entry. So multiply 1 by 2 and add in the third row. So 2R1 plus R3. So I apply that and I end up getting the next matrix over here. So 1 0 0 the first column, negative 3 1 2 the second column now. Why? Because I multiply the first row by 2 and add it in third row. So when I multiply the first row by 2, I got negative 6. When I add it in 8, I get 2. And in the same way, multiply the first row by 2, we get 2k. Add it into the third row, I get 2k minus 3 over here. Now we go and make these two 0. To make these two 0, I have to do these operations. Multiply the second row because now the pivot entry is over here. So I multiply by 2, 3 and add into the first row. Then I multiply by negative 2 and R2 and put it in, add it in the third row. So that gives me this matrix. Now looking at this matrix, remember we had only 2 variables or 2 columns of the coefficients or the matrix, and the third column was the B vector. So we end here. So what does that mean? So if I try to write my solution, I am getting C1 is equal to negative 15 plus K. C2 equals we get from here C1 equals negative 15 plus K and C2 equals negative 5, but we don't have any C3, so what the third row gives us is 0 equals 7 plus 2K. Now if 7 plus 2K is a number other than 0, then this system is inconsistent, and then we say that Y is not in span AB. But since we can have if we set it equal to 0, what we get is K is equal to negative 7 over 2. So which means this value of K will ensure that Y is in span of AB. Okay, so that's all for section 1.3. What we learned here is that finding whether a vector is a linear combination of the given vectors, we have to solve the system of equations that we learned in section 1.1. And otherwise, if we are checking whether a given vector is in span of some given vectors, again, it's the same thing. We have to solve the system of equations.